So we're going to start our gas unit off talking about the ideas that you learned during first year. So hopefully when we get done with this, you will have a good memory of everything. So starting off, we're going to refresh your memory on the kinetic molecular theory. These are several ideas that allow us to picture what's going on inside a gas. So what are the molecules doing? How are they behaving? What's happening? So first idea is that gases consist of large numbers of molecules or atoms that are in continuous random motion. So every molecule is constantly moving. There's no pattern to how they move. They collide with their walls. They collide with each other, but they are in constant motion. The other idea is that that gases are mostly empty space. The molecular volume of the molecules themselves is negligible compared to the space between the molecules. So we don't we don't worry about the fact that the molecules take up space because they're just very small. Third idea, molecules don't attract or repel each other, so if they come near each other, they basically ignore each other. Fourth idea, if there is a collision, collisions are considered elastic, which means no energy is lost when two molecules collide, or even when the molecule collides with the side of the container. No energy is lost. And the last idea gets us into temperature. So a molecule's average kinetic energy is proportional to their absolute temperature. So that means, absolute means we've got to start dealing with the Kelvin scale. So just a review quickly of those four variables that the kinetic molecular theory kinds of leads us into. Pressure is a measure of molecules colliding with the walls, the force that the molecules hit the walls with. So we're not talking about the particles colliding with each other, we're talking about the particles colliding with the walls. Units, you see there, there are several ATMs. They're equivalent in kilopascals or just straight up pascals. PSI is the unit we use when we talk about filling tires, car tires or bike tires with air. And then finally, the barometer unit, 760 torr, or you probably saw it more often as 760 millimeters of mercury. That's the unit we use when we talk about barometers. Second variable is volume. Not too much to say about that. The volume of the container, milliliters, liters, N number of moles of gas, related to the mass of the sample, and then T is absolute temperature. So basically what we're saying is the temperature of the gas is 100% proportional to the kinetic energy. So what that means is if the temperature is 0, molecular motion has stopped. At 0 degrees Celsius, that's not true. So we have to use the Kelvin scale in order to show a true correlation between absolute temperature and molecular motion. The equivalent between Kelvin and Celsius is to add 273.15 to Celsius. We're actually not going to worry about the 0.15. We'll just drop that off and we'll just add 273. Okay, once we learned the variables, we started taking a look at how those variables interact with each other. In order to do that, we had to consider what would happen with two variables if we held the other two constant. And what we came up with after we started looking at all that stuff is what we refer to as the combined gas law. And you can obviously see it there. The way it is set up and the properties that we notice, that there are direct relationships between temperature and volume, pressure and temperature, moles and volume, and moles and pressure. So what that's saying is if temperature goes up, volume goes up. If pressure goes down, temperature goes down, and so on and so forth. So I want you to notice in the combined gas law equation, all of the relationships that are direct, you see they are divided one by the other. That's going to be indicative of any relationship that's direct. To show a direct relationship mathematically, you're always going to show a division problem. On the other hand, there are two inverse relationships, temperature and moles, as well as volume and pressure. And notice on our equation, those two variables you see multiplied by each other. And again, that is indicative of an inverse relationship. Anytime you want to mathematically show a relationship between two variables that are inverse, you're going to show a multiplication problem. So that's kind of good to keep in mind. We've seen that before with concentration when we did dilutions and so forth, but it's a good idea to keep in the back of your head. Okay, so not all of these variables are going to be changing simultaneously. Some of them are going to be held constant. And so some of the key phrases to look for in questions, if you've got constants, would be something like this. So if the number of moles are going to be held constant, you've got a sealed container. So a lot of times that's what you'll hear about. If volume is constant, the container will be rigid. So there's a key term to look for. If you have constant temperature, it may say something about the container being insulated. And finally, if you've got a constant pressure, chances are that you have a flexible container because the volume needs to move if we're going to try and keep the pressure constant. So those are just some key phrases to look for when you start working with problems. All right, so here's a couple of examples of using the combined gas law. So Boyle's law just asks you to look at pressure versus volume. So we take our combined gas law equation, but in order to compare pressure and volume, we want to hold moles constant and we want to hold temperature constant. So then we can rewrite the equation as just P1V1 equals P2V2 and see what happens. You will notice that in this example, as the pressure increases, the volume actually has to decrease in order to maintain that. Charles' law is another relationship that's volume versus temperature. And once again, if we're going to compare volume and temperature, we need to keep moles constant and we need to keep pressure constant. So once again, we could rewrite the equation to look something like that. And here you see that Charles' law is a direct relationship. As the temperature goes up, the volume also goes up. All right, so let's practice a little bit. So here's a problem. I'm going to suggest that you stop the video, give yourself a chance to practice it, see what you come up with. There's a typo. See what you come up with, and then continue the video and see how you did, because the answer is going to be right down here. There's going to be a few more problems. Like I said, I would pause it, make sure you can do them all. So since we are only comparing volume and temperature, here's our equation simplified. Volume is what we want to solve for. I am going to ask that you do this kind of rearrangement of the equation before you put the numbers in. Then you can quickly put the numbers in and solve for the value. Second question, you've got volume and you've got pressure changing, constant temperature as well as constant number of moles. So equation is going to be P1V1 equals P2V2. Again, please isolate the variable before you plug the numbers in. That is going to be an expectation that I'm asking for. Plug the numbers in and you get 53.0. So I'm trying to maintain sig figs here, doing a reasonably okay job. Okay, next idea we talked about was the idea of standard conditions. Those are conditions that we have agreed upon to call standard. And you may or may not remember that standard conditions are 1 ATM, 273 Kelvin. That's referred to as STP, standard temperature and pressure. If you have 1 mole under those conditions, 1 mole is the standard value. And if we set those 3 conditions, the volume that you get is something called standard molar volume. And you may recall that that equals 22.4 liters per mole. So if I have 1 mole of gas under STP conditions, that 1 mole of gas will occupy 22.4 liters. So this is a very important conversion factor that you're going to see used in problems to come. Okay, next idea. What if we've got a situation where the conditions aren't changing? We don't even know what they all are. We can't use the combined gas law because we don't have 2 pressures, we don't have 2 volumes, we don't have 2 temperatures, and so forth. What are we going to do? Well, you may remember that we are going to set one side equal to the standards because we know a set of values are always going to be true. 1 ATM, 22.4 liters, 1 mole, 273 Kelvin, will give us one set of standard conditions. So if we set the one side equal to standard, we could calculate this out. What you wind up with is a value that is 0.082 liter atmospheres per Kelvin mole, because we've got to include all 4 of those units. None of the units have canceled. So you wind up with a value that we learned was R, the ideal gas constant. So that's how we got then the ideal gas law, which is, as hopefully you know, PV equals nRT. So R is equal to PV over NT. That kind of is the combined gas law idea, but for us it's much easier to remember it this way, PV equals nRT. That way you don't have to worry about manipulating the equation as much if it's everything in the numerator. R is a couple different numbers depending upon the units that you use. The 2 numbers that I am always going to provide you is 8.314, that is joules per Kelvin mole. A joule is kilogram meter squared per second squared. It is a, here's another version of the units that we don't really ever use this set, but this is what we typically use. And then the 0.082 are that you are used to seeing. So these are the 2 numbers that I will typically give you. So if you are given a pressure that is not ATMs, you're going to have to convert them into ATMs in order to use them. You have to have volume in liters. You can't use volume in moles. You have to have temperature in Kelvin, although you should have temperature in Kelvin all the time. So this R is the one I'm going to give you. We could look at all of the other possible units. You can see them up here. What if I have calories? What if I have torr or millimeters of mercury? You can calculate the value for R in any set of units, but like I said, these are typically the 2 that we're going to use. All right, so I'm running out of time. Got one sample problem to do. I think we can get it in. Go ahead and see if you can solve this. So we're doing a chemical reaction to produce some CO2. How many moles of CO2 are generated if we have these conditions? So we're looking for N. So PV equals nRT. Rearrange the equation to get N equals PV over RT. Fill in your numbers, again making sure that you have the right units. This time atmospheres works. Kelvin or Celsius has to go to oh, that's a typo. I did 32 instead of 23, so that answer is probably wrong. Have to fix that. So calculate what it is actually supposed to be. We'll tell each other in class. And then we solve for N, the number of moles. So notice liters cancels out, ATMs cancels out, Kelvin cancels out. We're left with 1 divided by 1 over mole, which puts moles in the numerator. All right, so we are going to quit the video here because I'm running out of time, and besides, we're going to shift to a new topic. So on to part 2.